You're about to listen to a new episode of Audio Signals. Get ready to take a journey into the known, the unknown, and everything in between. Recorded at no specific point in time nor space, ITSP Magazine's co-founders Marco Ciappelli and Sean Martin follow their passion and curiosity as they venture away from the intersection of technology, cybersecurity, and society to discover new stories worth being told. Knowledge is power, now more than ever.
Nintex is the global standard for business process management and automation. The Nintex platform helps their clients accelerate progress on their digital transformation journeys by quickly and easily managing, automating, and optimizing business processes. Learn more at nintex.com.
Blue Lava is the first business platform for CISOs to manage their security program. Blue Lava guides security leaders to effectively measure, optimize, and communicate their security program with confidence and ease in one platform. Learn more at bluelava.net.
I pushed the button, Sean. I don't know.
Where's that button taking us today?
I don't know. It's red. It has a count. It's not a countdown. What is the opposite of a countdown? A count up?
It's just a clock, timer.
Timer. There you go.
Is there an abort button here?
I think there is.
There's always an abort button during a launch sequence because everything can go wrong, just like the podcast.
Exactly. We'll have our finger at the ready for that one today.
Well, there is that button that I pushed that is now red. It says end broadcast, so I know that if I push that, I can stop this. But would you want to stop it when you're already up in the air? A rocket that would not. Be good.
It's a very expensive abort sequence, but yeah, if you hit that, and it will detach you from the first stage, the launch vehicle. It will detach the spacecraft and its housing. It'll rocket you up a little bit further and away from the first stage itself, and then you just float down and your parachutes deploy. But it's very expensive because
you're trashing a lot of cash.
Yep. Yeah, you just
and hopefully it's a nice gentle float down.
Yeah. Well, yeah, unless that rocket is retrievable, you kiss that first stage goodbye. And even if it is retrievable, it's like, you know how much gas you just burned up? And gas ain't cheap right now. So
that's for sure.
Yeah.
But then there is the old next generation, with SpaceX, that they come back and they launch a lot of them. So eventually we can talk about that. But Sean,
and battery-powered
rockets. We're going to space.
Mm-hmm.
Are we going to space?
Battery rocket?
Battery-powered rockets, yeah. And we don't have to waste gas.
That'd be great.
Right?
Well, there is some of that in stuff that is already up there. I mean, that's how they get the energy to go, right? Solar panel, a lot of them. But I don't think that there is the energy to put them up out of the gravity.
Not quite enough oomph
in
that.
No.
Yeah.
I don't think so. So everybody listening, you already heard the voice. Hopefully you heard our first podcast together. And it's Matthew Williams. Matthew, thank you for joining us again.
Hey.
Great to have you on again.
Thanks.
Yeah.
Love to.
So last time we went into the future of education, and then we found out that you actually do a lot of writing about space. You're a writer and curator for Universe Today, interested in engineering, a contributor, Stardom Space, Stellar Amenities, and then you're also a science fiction author. So we're like, hey, please come back. Let's talk about space.
We enjoyed it, and we like these topics. So let's do it.
Yeah, my favorite topic, it's favorite place to be.
How that happened? I mean, let's start with that, and then a little introduction again about yourself, more than what I said, if it's not enough. But where did this passion for space come from? Space?
It's hard to say, but I grew up in the 80s, right? I was exposed to Star Wars, Star Trek, and some of the best science fiction literature around, and it always got to me. It always lit a fire. And by the time I was a teenager, I started actually being able to appreciate a lot of what I'd grown up with. I was like revisiting all the books and movies and stuff, and realizing that, oh, I can appreciate this on a new level, because I'm now old enough and mentally mature enough to appreciate a lot of what they're saying and the points they're making. And somewhere along the line, there was a class in high school that really kind of helped click it, and it was we were studying sort of the way technology and society are come together and the impact it has. And yeah, I was really blown away by that. And I felt like when I got to university and I was studying the history of science, I felt like there's so much here I don't know. I feel like a rank amateur. I like that feeling, because it's like you just want to pursue, try to find answers, and yeah,
that's my first question to you. Mm-hmm. Are the answers in space, do you think?
Yes. Yeah? I think the answers to all our questions are in space. And it's not because it's because, of course, life in the universe is directly linked to life here on Earth. Our activities are in both space and on Earth are completely and utterly linked. There's no separation, right? There's this attitude I've felt, and I've seen this a lot in recent years, that activities on Earth and space, these are two separate domains, and you can do one or the other, but not both, right? Shouldn't we fix Earth first is the biggest question I ever hear. And it's like, they're not separate. What makes you think they're separate, right? And if we're going to succeed up there, any success we have up there is going to be directly applicable down here. But that's a whole nother. To quote Dr. Cyan Proctor, she says this quite a bit, and I've heard other people saying it too. Solving for space solves for Earth. And she went up on the Inspiration 4 mission there. She was one of the 4 citizen astronauts. And so I quote that anytime I can, and I'm always attributing it to her, because it's like, well, that's where I heard it. And as far as I know, she invented that.
Well, it's the equivalent of all the research in Formula One gets applied to other driving things, right? So you have to have that other view of things too.
I love that, because I like Formula One, but I think for space it's a lot more philosophical than that. But it's a driving force for sure for innovation. But I think that where you just went, Matthew, with the philosophical approach, is to learn about ourselves, to learn about the origin of everything. Yeah. And I'm gonna break a news here: it's not 42 the answer.
Yeah,
42.42.
maybe that. Let's stay there. So there is different way to know the universe, to explore, and one is to actually go there, which we know is not that simple. We talk about the abort and the big rocket, and we're going back to the moon, which could be a topic for another conversation, that's for sure. But a way to go to space, the oldest way, the safest way, is to look up into space. And I think that's today should be the core of this conversation. We said we'll talk about the Webb telescope, but there are a ton of other telescopes out there. There are telescopes here. I live in LA, and I did a trip to Mount Wilson where Hubble did the research 100 years ago, whenever that was. And it blew my mind just to be in that place where this happened, right? So tell us, what do we see when we look up in the sky? And how many ways there are to look up in the sky?
Well, good question. So the second part, I think first, there's any number of ways, but the two chief ones are to look through ground-based telescopes, right? Here on Earth, big observatories, big primary mirrors that are going to look up at the night sky, and they're going to see, our solar system and distant objects without the interference of the sun, of sunlight, right? As a kid, I often wondered that. It's like, why is it that the stars come out at night? Obviously, it has to do with the sun setting, but why is it that they're not visible the rest of the time? How does this work? And yeah, it's like, well, light is reflected by our sun, and when it's in the sky above, it drowns out all that background light. And we're seeing, once it sets, and if you live in a place without a lot of light pollution, you have the added benefit there. It's like you see clearly the cosmos, and not as it is, but as it was when all that light first left all those sources, right? The second way to see it is from space, and like you said, going to space and looking at it from down here, those are separate things. But it was Nancy Grace Roman, who was a seminal NASA researcher, and she's called the mother of Hubble. She was the one who first proposed how a spacecraft observatory, like Hubble Space Telescope, how it could be the best of both worlds. You send this telescope into space; it orbits the Earth, or at either in orbit of Earth or at a Lagrange point, one of the stable points, and you can look and survey the universe, but you don't have to worry about any atmospheric interference either, because that's one thing ground-based telescopes always have to deal with is atmospheric interference, right? As light passes through our atmosphere, it gets warbled and distorted, and we can get around that. There's adaptive optics, as they call them there, which will correct for that, but otherwise anything you see you have to accept is going to be just a little distorted. So those are the two chief ways we look at the universe. What we're seeing, we're basically seeing space-time. We're seeing the past. Because no information that's coming from that kind of distance is current. So basically, we're looking through time as we are looking through space.
Yeah. And what I was referring to about different way to look is, there are different kind of telescope that sees different things. So infrared, you do like audio signals telescope, you do a lot of other things, spectrometers and whatever. So why do we need that? And I'm asking questions as thinking what the audience may want to hear, right?
Well, absolutely. You're right. Sorry, I didn't clue into that.
No, that's totally clear. It's too much to clue in.
Optical telescopes, as we would call them, or the optical filter, you're talking about visible light, and that means light that comes in all the colors of the rainbow there. But as scientists have known for quite some time, it's that there is this huge range on either side of the visible spectrum that is not visible. You can't just see it. I believe it was Isaac Newton who did this. He installed a prism over this little hole, so sunlight was shining into this room just through a tiny hole. He put a prism in the way, and so that broke the light into colors, and then the colors were then projected onto this table, and he put thermometers on them because he wanted to see if different colors of light corresponded to different temperatures, and he found that they did. And but at the blue end, things were ever so slightly cooler. Down to the red end, things were warmer. But then one of his thermometers was not getting hit by any visible light, but it was hotter than all of them. And from that, they realized there's something beyond the color spectrum here. And so all the research we've done, it's like, there's infrared, which is on the other side of the red end of the spectrum, and that's heat. If we go on the opposite side, beyond blue and violet, we have ultraviolet, right? I mean, they put it right in the names there to let you know where on the spectrum it is. And yeah, and you also have X-rays, gamma rays, etc., microwaves. And yeah, it's like the shorter the wavelength, the more harmful it can be to you, to your cells. But otherwise, yeah, it's like, well, the human body can handle all kinds of radiation in limited amounts, and that's sort of the double-edged nature of the cosmos and our sun. It's shining light in all directions and radiation in all directions, and some of that, it has the power to give life and to kill it. So the reason why we look in all these different filters is because the only smart way I could put it is to say we want to see all of what's there, because if we're only looking at visible light, we're only going to see what is visible to us, what our eyes can discern, what is making it to us in spite of all the interference or dust and gas that's absorbing it. So James Webb in particular, it's equipped to do spectronomy. It's going to be looking at dust and gases and solar systems in formation, and it's doing that by looking at the heat that they emit. And then its spectrometers look at that and say, well, I see these chemical elements and that. And that's going to be very important to searching for life, because, yeah, it's like we can only really identify life by identifying the chemical signatures of it. So that's why we do it. And yeah, in that respect, it's a successor to Hubble. It's a successor to Spitzer. There are other observatories like Chandra and Compton, which look for X-rays and gamma rays, and they're going to have their own successors in the future. But this one is picking up where Hubble where Hubble still is working there, and it's going to focus on the infrared. And by picking out signatures of heat in the universe, yeah, it's like wherever light got absorbed and not enough, we can't see enough of that being re-emitted, we're going to look in the infrared and we're going to see the bright patches where all this energy is being soaked up. And these things which we otherwise couldn't see are now visible to us.
Maybe, yeah. Can you talk to me a little bit more about what we see? Because there's the visible light, which we can actually see straight away. That's us looking through a telescope, right?
Mm-hmm.
And then there's the translation of what the device and perhaps some compute power can take that information and translate it into something we can see through our eyes. Mm-hmm. So I'm wondering, maybe at a high level, how does that work for each of the, maybe generally speaking? And what I'm really curious about is how that information is captured. Because when I'm looking through a telescope, it's real time. It's through my eyes into my brain. I might remember it. Eventually I'll forget it. And I think the value of this is the ability to record this information, translate it so we can actually see it as humans, maybe refer back to it, look at changes over time. So talk to me about that whole process of translation and storage and using that data long term.
That's hard. It's a little outside my wheelhouse, but I'll do my best.
Okay.
I reserve the right to feel stupid here. So no matter what you're doing, you're looking at photons, right? And photons have different wavelengths. They're a particle and a wave at the same time, right? And as they're passing through your optics, depending on what filters you've got in place, they'll register, right? Now, with an optical telescope, it used to be they would take photographs, right? Have photo paper there, the light comes in, the photons hit in this pattern, so now we have a picture of like Jupiter or Pluto, right? Light bouncing off of it and into our telescopes there. But the way we do it today is it's similar, but the images are acquired by a computer. They're digitally rendered, and depending on the filters you use there again, right? It's like, we're separating different wavelengths of light into different filters. when we recombine them, we create a color image of what that looks like out there. And if we also have filters there that can intercept infrared photons, and then that's going to show up there too. And in order to, rendering that again, requires a computer there, and it's showing, well, this is the pattern of the light. It glowed like this. And once you add color to that, and infrared imagery, they'll usually they'll use red, orange, yellow, and white there to show the hottest points, and green and blue to show the cool spots. Yeah, once you render that, it's like, yep, we're looking at this big heat source here. If it was something we could see, it would glow that brightly. Yeah, that's basically what we're seeing. It's just patterns of photons that then have to be digitally or photographically rendered in order to make sense to our eyes. Yeah, that's the best I can do there.
Oh, that's perfect for my simple brain anyway.
Okay.
Well, it is about breaking it down on an understandable way, right? I mean, we don't we're not the physicists that do this kind of stuff, but at least we have a grasp of you more than us, and then we ask some questions. Some are stupid, some are a little smarter than other. So
mine are stupid, yours are smarter than others.
Pretty close. I was cutting pretty close there. I should add that a lot of images are taken. They're black and white originally, right? They're taking in light. They're discerning between the presence of light and the absence of light, and it's just black and white. And then they will add colors to it in order to show, what parts of the spectrum were coming through here. This is how it would look to the naked eye if your eyes were really high definition, And it's often exaggerated, but just to give you a sense of what colors and what elements are there, because that's the other thing. Light comes in many colors, often because of the chemical structure of what is absorbing that and radiating that. Not often, always. So if I see a big red nebula, it's like to my naked eye, it actually wouldn't look all that red, but in astronomical imagery, they would add red to it to say, that's a hydrogen-rich nebula. So red is the color that we would be seeing, because if we look at it through a spectrometer, then we'd be seeing little lines around the red end of the spectrum there. Which is, again, that comes back to what James Webb is going to be able to do.
Yeah. So let's talk about the James Webb, because so they put a folded origami on a big rocket, and they shoot it up in space, and then they reach in some sort of place where there is a specific point, like the Lagrange point, if I remember well. It's going to stay there. It's only 1 million miles away, and then it's going to be unfolded. Well, it is already being unfolded successfully, and now they're actually focusing all the different lenses, and I've seen the picture of what it looked like a week ago and what it looks like today, and it's it's like, I'm turning the wheel, it's getting on focus. And so is that crazy? I mean, you can even go there and fix it like you did on the Hubble. If something goes wrong there, that's a lot of money just hanging. So why do we take that risk of why are we there yet?
I'd say that the answer to that question, it's the same for because everybody was asking this, why are we still funding it if with all the delays and all the cost overruns, right? And it's like, well, the reason there are the delays and cost overruns is, they have to make sure it works perfectly, because if they send it up and it's not, sending a servicing mission is not an option here. It doesn't have, astronauts can't just hop aboard it like they did Hubble and straighten the lens out. And that was really expensive, by the way, that mission.
That was fun.
The reason why is the payoff. It's like this telescope is our most powerful, most complex most capable mission to date, and it's going to be followed by several more next generation telescopes. But the capabilities it has are pretty special. So it's going to be one of our most important observatories for quite a while, I think. And just getting there. Like you said it perfectly there. Are we there yet? Yeah, getting there is, it's like we won't even begin to really appreciate just how much this mission will mean until we turn on and start really seeing what's out there. But it's like NASA and all the people who contributed to it, they know what it's going to be looking at. And, the rest of us who've heard the descriptions, we have some idea of what it's going to be making possible. So it's like, we got to get it there. Yeah, we spent so much money on it already, but that only seems to motivate us to keep going because, it's like this has been too expensive and too big to fail. And the payoffs are going to be so immeasurable, we can't not get it out there. Yeah.
So I was hearing a podcast the other day, actually, with John Mather, which is the Nobel Prize physicist. That I think is senior, if not the guy that runs the whole James Webb operation. And somebody says the expectation is to show that it's worth the money that we spent to put it there, is to actually get a picture of the Big Bang. Oh. And I think it's kind of like, I don't know, what's your take on that?
Well, the James Webb is not actually going to be able to see the Big Bang itself unfolding. It's going to be looking back through space and time to some of the earliest periods in the universe. So we're going to see the results of the Big Bang for sure. We're going to see the earliest galaxies in formation, and the first stars, the earliest stars, and the first planets. Now there is still a limit to how far back we can see. Among its objectives is to see the first light in the universe after the Big Bang, or the light from the first stars and galaxies, right? Anything, and in doing that, it's piercing what's known as the cosmic dark ages. We've had a hard time penetrating that with our instruments because it's like light from this period has been shifted so very far. It would really only be visible to us today in what's called the 21 centimeter radio emission domain. And that is, that's rather hard for our instruments to pick up. And this is caused by the fact that during this period, the universe was permeated with hydrogen that had been created from all the heat and radiation unleashed by the Big Bang. As that formed into stars and galaxies, the light of these stars and galaxies dispelled those clouds, and so our instruments today are able to see that. But so much was happening when the universe was still shrouded in all this mystery. We want to be able to pierce that veil and see the first stars and galaxies in formation. And the James Webb is going to be the first telescope that is, that can do this in a dedicated way, because it'll be able to pick up the emission lines that correspond to hydrogen or to the radio waves emitted by hydrogen.
I ask the questions that I have absolutely no clue. So thank you for explaining that. And I know there is way more on the table than that. But what is the thing that strikes you the most about the Webb telescope? Is it something about the actual power that it has, the fact that we were able to place it where it is without controls, or I don't know, but what's the big breakthrough here? Then you say many more, even more powerful, are going to come.
Well, absolutely. It's power, but what really blows me away is its complexity and its sophistication, and that's part of why it took so long to get ready. It's like we need an observatory that can be, because it's an infrared observatory, it needs to be able to stay very, very cold, so there's no heat interference that's going to throw off its mirrors. So it's got to have that big complicated sun shield, and that's got to go through a big complicated deployment. The mirror itself, right? The 18 segments, they're all beryllium and shiny gold colored. Those two, right? Those have to be all perfectly aligned, and it's got to fold into place. And then the secondary mirror's got to deploy in front of it. And yeah, it's like the only way you could send something this big up there is to make sure that it can fold up and scrunch down into this tiny little, well, not tiny, but smaller vessel, and you can fit that inside the payload fairing of a rocket and launch that up. But once it gets there, it's going to have to unfold again. And they had to do that on Earth over and over and over again to make sure that it would unfold the right way in space. So, in a lab, they're doing that. In a vacuum chamber, they're doing that. And it's just like, yeah, this has to be, there has to be no margin for error here. So yeah, it's a wonder we're able to do it at all, because it's just so complicated. You'd think most people would have given up and quit a long time ago. But again, it's like the payoff, man, the prize. And also, God, we spent so much money on this already. Let's just, let's get it done. But that blows me away for real.
Yeah.
So I'm wondering how does that fit into the big picture of other research being done using telescopes from Earth? Does this eliminate the need for some of those? Does it enhance that work? Does it change how we look at these terrestrial devices, and maybe innovate and enhance them in ways we hadn't thought of before?
Wow, that's a very, very good question. Enhance. Because what it's going to do is going to be complementary to a lot of what a lot of telescopes are going to be doing here on the ground. There's several. Every time I've written anything about next generation telescopes, I always have to include the ground-based ones. I got to mention the big three here, like the extremely large telescope, the Giant Magellan Telescope, and the 30-meter telescope, because they're all going to be involved in this. James Webb is going to be very good at spotting extrasolar planets by the light that they emit, right? The light that's reflected off of their atmospheres and their surfaces. It's going to spot them with its infrared optics, and then these ground-based observatories are going to do the follow-up observations, looking very closely at them and saying, so that light we see coming from that exoplanet's atmosphere, what chemical signatures are there, right? And Webb is going to be able to do that too. It's going to, it's got spectrometers galore, and it's going to see the patterns of the light from those atmospheres. But the ground-based ones are going to be doing this as well, and they're going to have employ these heavy-duty coronagraphs that are going to block out the light from the sun that would interfere with any readings. They're going to have their adaptive optics there to make sure they got a pristine view of it, and they're going to be the ones spending lots of time in follow-up observations characterizing the atmospheres. And that's a huge leap, because exoplanet studies have been about discovery for the most part until now. And it's like, well, now astronomers have been making the transition to looking more closely at the ones we've already found and already confirmed, and saying, okay, so what's there? What's the atmosphere made up of? Is it actually potentially habitable or not? And these new instruments, they're going to pick up that thread, and they're going to say, well, we can see an atmosphere that's rich in nitrogen and oxygen, so that's a good sign. And we're also detecting the chemical signatures of carbon dioxide, so it has a greenhouse effect, but it's a lot of carbon dioxide. So maybe somebody's there pumping that into the air with factories and fires and such. And it's like, oh, that's that's not only pointing the way to life, it's pointing the way to technology, to civilization. And they're a lot like us, they're ruining their planet. That's, they're pretty stupid like us. Yeah, so it's going to be complimentary. And when Nancy Grace Roman telescope goes up, named after Hubble's mom, it's going to be Hubble's truest successor in every sense, and it will be working with James Webb as well. In that case, it's the Nancy Grace Roman that's going to spot exoplanets in large numbers, and James Webb is going to do the follow-up. But they're all working together, so nobody's doing everything, and it will ultimately, because of limited time. Every observatory has a certain amount of time of observing hours, right? So different scientific teams need to book time. Mostly they just consult data that was gathered during a certain survey. So the fact that an observatory's time is very precious is one of the best reasons for having multiple observatories doing multiple things. Yeah.
That's interesting, actually, and I think we can start wrap with this, because then you go to exoplanets, so you start having questions about alien life and why we do that, and a lot of theories out there. But let's not go there. Although I would love to talk in another episode, maybe focus on exoplanet.
Oh God, but yes.
I'm interested in the space, in the time allocated. So if you want to go and look through the James Webb, can you do it? Who is doing that? I mean, apart from the people that put it out there and NASA, I mean, I was hearing that there were schools applying for that, college research center. Do you know anything about how these happen?
Not really.
Okay, well, that's good. Me neither.
What I do know is there are resources for this. So I'm posting there a link to the NASA website, the NASA's James Webb Space Telescope site, I do believe they cover who will be able to access information from it, because of course, this information is meant to be shared, and in terms of who can't, I'm not sure. Certainly, the participating space agencies have their fingers in that pie there. They can draw on that information there, and any accredited academic university can do that as well. But I'm pretty sure citizen astronomers are also able to access that information.
Or at least you can access, like you said, you may not be the one that is requesting the task, but you can get the data collected by other.
In terms of who is setting the priorities, right? In terms of
that was more of my question, I believe.
That would be the space agencies involved there. So NASA, absolutely, they will be saying, in this particular campaign, James Webb is going to be looking here. Data will be provided. It will be made accessible from this campaign, and here's where you go to get it. As to what requirements you need to meet to gain access, well, there are some. It's not just anyone can access it. But
I have so many questions in my head because I'm not versed in this space, pun intended. But we don't have time to dig into it all. So I think we definitely have many more conversations here. I'm all about the technology and how things work and the data and ultimately what the outcome is. And I know you kind of hinted to some of the things, but beyond discovery and learning, what do we do to actually take action with the information that we're gathering? Does it impact climate change? Does it impact the way we power things? I don't know. There's probably a gazillion ways we can take this, all spinning around in my head at the moment. But I mean, just to get an idea that there are multiple types of telescopes and visuals and collecting that information, translating it for us to understand our ecosystem better is super cool to me.
That's a very good question. And the implications of that, are profound too. In terms of what, like, actionable stuff, well, for example, James Webb is going to be looking for exoplanets. It's also going to be looking in our own backyard for interstellar objects, for asteroids and asteroids that we haven't seen yet, and comets. It's going to be looking for life. Part of the mission is astrobiology, so it's going to look at moons like Europa and Ganymede and Enceladus and Titan and others, because these places are thought to have oceans in their interior which could support life. So that will directly and drastically impact the exploration of those. That mainly has to do with the future of space exploration. It's not really applicable to climate change, but it will tell us if any missions headed for Europa, you don't go through the ice, right? We've confirmed that there are biosignatures on the surface. They're coming up from the interior. Nothing can survive on the surface, but there's got to be life down beneath. So, if you're going to land on the surface, in fact, maybe don't land on the surface at all. Stay in orbit, fly through the plumes, pick up all the scientific data you can from them, and then just come on, and then transmit that back and crash. Not on the moon, though. Crash in Jupiter's atmosphere, right? It's like if we find life out there, we have to be extremely careful about the possibility of contamination. If we spot any objects in our solar system, as some have suggested there, they don't look natural. They look like they're actually probe-like, or they look like they're pieces of something that someone built. If in fact a Muamua was an alien and extraterrestrial sailcraft, and our solar system gets thousands of such objects passing through it, or has had thousands passing through it since it first formed, and some of them actually stayed, well then, it's like we need to. That's going to have huge implications for the search for extraterrestrial intelligence. I'm having a hard time finding an application for climate change. But it's like, all this research makes us appreciate where we are in the universe, right? So, it's like, looking for technosignatures abroad. It's like maybe this will get us thinking and talking more seriously about curbing emissions, because we see this on other planets there, and some of them look pretty dead now. We would like to avoid that prospect.
Yeah.
But
to end these, as we're running out of time, I would say, even just we started with the idea of the Formula One, developing then our cars. I mean, just think about the technology that he went to put and test and the whole design system to actually put the James Webb Observatory where it is. The fact that it is working so far is actually working perfectly, and is not even completely all set up yet. I mean, all that technology, all that know-how, it can bring, I'm sure, somehow bring back to our everyday use. And for many things that we don't even know. I mean, we know that a lot of stuff developed by NASA for astronauts, we're using it every day. We sleep on it. We do other things. So
the full list of applications there. That since the Apollo era, NASA spinoff, they keep track of that, and thank you for mentioning that. That slipped my mind there. Because Sean, the commercial applications from all space research there, right? I mean, the technologies, the ideas that's made available for free to the commercial sector to develop everything from medical treatments and processes to just knickknacks, gadgets, and so forth that make our lives easier or more complicated, whatever. So no matter what, it's like James Webb will have lots of applications, many of which we're probably already using. That will better life for people on Earth, and that's always the way it's been. So
And that's what a lot of people are doing on the International Space Station as well. And
Yes.
and then there is the other conversation about commercialization of space and a lot more things. So I'm going to draw a line here, Sean. I think we've learned a lot today.
Abort.
I'm going to abort this conversation. No, I'm not aborting. I'm going to actually, at this point, if you've heard it this far, it means that it was not aborted.
All right.
And we got to the end of it. We're just pausing it. We're pausing it, Matthew. And hopefully we'll pick it back from here. Maybe we'll bring even some more, maybe some guests to talk it over with us. And we just love to talk about space. So I'm up for that. I'd
love to talk about exoplanets. I mean, that is a wonderful, rich field. And I can't wait to see what James Webb has to say about just even planets next door, especially the planets next door.
And by next door, everything is very relative here.
Oh, yeah.
Still talking about a million of light years away.
There's an app community for that, next door planets.
Mm-hmm.
Oh, yeah, there is.
I think so. Yeah.
All right.
It talks about the dog that got lost, and they need help finding the dog. The planet next door.
All right. Yeah, the closest ones are just over 4 light years away, though, in Proxima Centauri. So, that is going to be really interesting to learn more about those guys. It's still, I mean, that's unfathomably far by our standards, but in cosmological terms, it's right next to it.
Exactly. Nice. All right. Sounds like we have another mission, Mark.
Yes.
We do have another mission, and we're going to push this red button again to end this conversation, and we invite you to check the notes. Matthew will probably share with us a couple of these links so people can check it out.
We already have one.
We already have one. We're going to have more, and stay tuned. We'll talk about space and a lot of other things on ITSP magazine, and in particular on audio signals, where we kind of go all over the places in space too. Thank you, Matthew.
Thank you.
Hey, my pleasure.
Blue Lava is the first business platform for CISOs to manage their security program. Blue Lava guides security leaders to effectively measure, optimize, and communicate their security program with confidence and ease in one platform. Learn more at bluelava.net.
Nintex is the global standard for business process management and automation. The Nintex platform helps their clients accelerate progress on their digital transformation journeys by quickly and easily managing, automating, and optimizing business processes. Learn more at nintex.com.
We hope you enjoyed this episode of Audio Signals. If you learned something new and this podcast made you think, then share itspmagazine.com with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our podcast channels. We hope you will come back for more stories and follow us on our journey. You can always find us at the intersection of technology, cybersecurity, and society, and some even beyond that.